Hello and welcome to my talk, A Faster Algorithm for Finding Closest Pairs in Hamming Metric. My name is Floyd Zweydinger and this is a joint work together with Esser and Kübler. As the title already suggests, we have together today a look into the closest pairs problem, which is defined in the bichromatic version by given two lists, L1 and L2, both of size n. Each element inside these lists is a binary vector of dimension d, and the goal is now to find a distinguished pair x and y in these two lists with relative Hamming distance gamma. This is actually a quite fundamental problem from theoretic computer science with numerous applications. For example, in cryptography or coding theory, we use it to decode random binary codes in the field of bioinformatics in the form of genome analysis, or in the field of machine learning as similarity search of images. It's therefore important to have a look into the algorithms solving this problem. And we start with the most fundamental one, the naive search. This algorithm simply checks every pair in these lists, meaning for every element on the left list we enumerate every element on the right list and check if these elements are our distinguished pair x and y. Clearly, such an algorithm has a runtime quadratic in the size of the input lists. Nevertheless, it's an important algorithm to state because we are using it later as a building block for our new algorithm. So as a next step, we want to have a look into the locality-sensitive hashing approach, or short LSH. This technique hashes similar elements with high probability into the same bucket, where afterwards one is able to search through these buckets with a naive search. So what does this mean? We choose a random hash function hi and apply it to each element of our two input lists, meaning we assign each element a hash value which uniquely defines the bucket where the element is put into. After we are done hashing every element, we are applying a naive search and hopefully we find the two elements we are looking for, x and y, in one of these buckets, in the same bucket. Note that because of the probabilistic nature of this approach or framework, this must not happen. This happens only with a certain probability. Note that in the case where the two elements are in separate buckets, we are unable to find them via the naive search. So in this case, we have to reapply a new hash function and hopefully find the value this time, the values this time. Another technique which extends the LSH approach is the so-called locality-sensitive filtering, or short LSF. In this framework, we are choosing filtering functions, a family of filtering functions fi, which we apply in the same fashion as in the LSH approach. Meaning, for every element we go through our two lists and apply our filter functions. Note that we are repeating this for n different filtering functions fi. Sorry. Because of the probabilistic nature and the locality sensitive properties of such a filtering function, it can happen that only maybe x survives, meaning is not filtered out in one of these filtering steps, or it can happen that they are in separate buckets, filtered lists, or it can happen that they are in multiple different filtered lists. But we actually need for our algorithm to succeed that the two elements x and y are at least in one of these filtered lists together. This whole filtering approach is then repeated recursively for every filtered list until we reach a certain depth. Just let's say in this simple example, the maximum depth is 2. So we reached already the end of the algorithm. And now, hopefully, if we have done everything correct, the filtered lists in the end are small enough such that we are able to apply naive search to find our two elements in one of the filtered lists in the last level. So let us have a quick view on the filtering function. Note that this whole algorithm is heavily depending on the choice of the fi. In our example, we are using the filtering function as the distance on certain coordinates to a randomly selected element. So every algorithm which is based on the locality sensitive filtering framework has a well-known time lower bound of n to the power of 1 divided by 1 minus gamma. And additionally, the filter functions also have a big impact on these two probabilities, namely P and Q, where P is the probability that any element V survives, meaning is not filtered out in one of the filtering steps or in one of the levels of this algorithm, and Q is the probability that both of our elements X and Y we are looking for do survive in the same filtered list. And it's actually one of our contributions that we are able to prove or to give a framework which allows us to analyze every algorithm or our algorithm purely on the two probabilities P and Q. So before we come to our results, let us have a quick introduction into previously best algorithm to have a better distinguishing between our algorithm and the old one. So on the left side, you see the algorithm. You see an image stating the runtime exponent for different relative weights gamma. You see our algorithm depicted in the solid line, and the algorithm by Otzarov depicted with the dashed line, which is also an LSF based algorithm and the previously best one, as I said. You note that from the beginning of the two lines, they behave exactly the same, meaning they are actually reaching the time lower bound of LSF based algorithms up to a certain point where somehow our algorithm runs off to the logical bound of n squared. And this is actually making sense because at this point, in expectation, if we are having two uniformly randomly selected elements, they have a distance of 1/2, meaning in our case that every element in expectation has the same relative distance as the distinguished one, which results in an algorithm which needs to enumerate every of such elements to find our distinguished one, and that's the naive search. On the other side, instead, the algorithm by Otzarov somehow runs off to a certain limit depicted with this vertical dotted line where it's still applicable. So this whole graph can be separated into two cases. The low density case, which we define as the case where x and y is uniquely determined by the distance gamma. In this case, both algorithms reach the time lower bound of LSF based algorithms. On the right side of the algorithm, instead, we are having the high density case, meaning there are more elements with the same relative distance as our distinguished one, which means for every algorithm, they need to enumerate every of such pairs to find the distinguished one. In summary, we were therefore able in our paper to state an algorithm which achieves the time lower bound in the high and low density case. We were able to significantly simplify the analysis of LSF-based algorithms. Additionally, we are allowing an analysis for different input distributions other than the uniform one. And last but not least, we were able to implement our algorithm and practically verify our results. So finally, we are able to have a look into our algorithm. So as before, we start with our two input lists L1 and L2, both of size n and dimension d. The first thing we are doing is we chunking every element into R equally sized blocks. Don't let you distract by the blocks that much. They are only an algorithmic tool to argue about the independence of the different levels we are about to see. The first thing our algorithm then does is applying our first filter function, namely the distance to a randomly selected element Z1 on the first block. This filtering is then, as in the LSF approach, repeated for n different randomly selected elements Zn. Note that in the first level we always enforce distance delta on the first block. And obviously we do hope that our two elements we are looking for, x and y, do survive in the same block. Note that because of the probabilistic nature, this must not happen. This can happen, but it doesn't have to. Sorry. And this procedure is then recursively reapplied to each of the filtered lists with the newly selected, randomly selected Zi, but now we enforce relative distance on the second block, meaning in the each iteration of our algorithm we enforce relative distance delta on block E. So we do now repeat this until a certain maximum level of R, because we only have R blocks. And again, we hope that our x and y do survive. And in the end, if we are done everything correctly, the filtered lists in level R are small enough that we are able to apply a naive search to each of these filtered lists to hopefully find our distinguished pair x and y. To be able to analyze this algorithm and the runtime, we need to have to take a step back and have a look into the two probabilities P and Q. So we are currently again looking into onto the first level, and as I said, P is the probability that that any element V survives the filtering step. But this is exactly the probability that V has a distance of delta on the first block to a randomly selected Z. Note that this distance on the first block is denoted by the subscription E in the delta operator. Exactly the same states for the probability Q, where we do want to find out the probability of the fact that x and y do survive the filtering step, which is again the relative distance on the first block. Well, on every block, but in the first level on the first block. And the cool thing is now that given only these two probability, we are able to state the first preliminary version of our theorem, which states if P and Q given as defined and let R be the depth of our algorithm, then we are able to find the distinguished pair in time maximum of the two values A and B. And to understand where these two values are coming from, we have to take a step back and have a look again onto our algorithms and how the sizes of the filtered lists do evolve during each enumeration step of the algorithm. So we are again looking onto the first level 0 of our algorithm. As a little help, I now state an additional value n, which states the number of leaves in each level. So we are in the in a level 0, meaning we only have our two input lists, therefore we have only one node in our tree. And now we have to ask ourselves what's the size of the lists, and clearly the size is n. The much more interesting question is now, how does this size of the filtered lists do involve? Note that we are creating we are applying n different filter functions, resulting in n leaves in our first level. And this, regarding the size of the filtered lists, P is the probability that a random element, any element survives, meaning in each filtered step only a p fraction of elements survives, resulting in lists of size n times p for the first level. If we reapply this analysis now for the second level, clearly we have only n times p squared elements which do survive the second filtering step. And because we are creating n new leaves for the previously already n existing leaves, we are resulting in a total amount of n squared leaves for the second level. If we go now further down the tree and have a look into the second last level, r-1, we have of course n to the power of r-1 leaves, and every filtered list in one of these leaves has the size n times p to the power of r-1. And we are actually able to prove in our paper that only if we want to calculate the runtime of our algorithm, we can prove that the majority of runtime, or the majority of costs of our algorithm is the last level. So to find out the cost of constructing the tree, we have to find out the cost of constructing the last level. In the last level, we have n to the power of r leaves. For every these leaves, we have to enumerate the previous list of the second last level, resulting in a cost of n to the power of r times a r-1, well, the size of this list, resulting in n to the small n to the times p to the power of r-1. Note that we are able to choose n as 1 divided by q, because we want in expectation that our two elements x and y survives in at least one of these buckets. So if x and y do survive with probability q, we want 1 divided by q tries that in expectation they do survive once. So if we replace n with q, 1 divided by q, we're resulting exactly in the value a. Meaning that in the theorem I just stated, the value a is nothing else than the cost of constructing the last level of our tree. Now the value b is actually not that hard to understand, because we are not just constructed the last layer. No, we have to apply the naive search on it. Meaning for every leaf we have to pay the size, we have the runtime of the size of the two input lists we are applying the naive search on, resulting in exactly the value b. We were able to prove in our paper that for optimal parameter choice, b is always bigger or equal than the parameter a, which further simplifies the analysis of our algorithm. And last but not least, if you want to adapt our algorithm for any other input distribution than the naive one, you only have to find out the value, the expected size of the two lists AR times BR, the size of these two lists, to adapt our algorithm. And now we are finally able to state the full theorem of our algorithm. So the algorithm I just stated you finds the distinguished pair x and y in time t, where t is in the low density case the time lower bound of any LSF based algorithm, and in the high density case the expected number of closest pair we do find in the two input lists. Thank you very much.